Today we're going to talk about inertia. It's basically a part 2 to the first video on inertia, so if you haven't watched it, I recommend that you go and watch it on the channel. It's the previous video. What we're going to talk about today is basically inertia, but we're going to focus on the idea of mass. And this formula still applies. And let me just sort of like end the reasoning, which I was about to sort of like move on to in the last video. Basically, you have this particle trajectory, and we're deviating the natural trajectory of the particle, and this natural trajectory we're going to label as the inertial trajectory, even though we have reasons to think that this is not really exact within the context of general relativity. But general relativity is one theory amongst many others. But there's very good reasons to think that this theory is correct. But we're not going to go into sort of like the epistemology of theories and what does this actually mean within science and paradigms in science. We're just going to sort of like take it for granted the classical mechanical point of view, according to which this is the natural trajectory of a particle unless it's acted on by a force, where the force is going to attract it towards the bottom of the board, and as a consequence, it's going to deviate the natural trajectory of the particle. So we're going to say in general relativity, I mean, this is the result of an acceleration. We know that force is a vector, acceleration is also a vector, so therefore it has a specific direction. If you're changing angles, then this vector, which is sort of like the velocity vector corresponding to this motion, which has magnitude and direction, well, by applying a force, you're changing direction, therefore you're accelerating the vector because it's going to be a different velocity vector, which we might call now v2. And this is just to highlight that changing direction is different from an inertial trajectory. Because this is an inertial trajectory, it's a state of motion, and this is a different state of motion as a consequence of a force. And therefore, the sum of the forces is not zero anymore. So, turning counts as a kind of acceleration, is what I'm trying to say. Any non-zero acceleration deviates from inertial trajectories, and therefore we're sort of like outside inertia. And I hope this is clear, and I want to bring to your attention another idea along the same lines, of course. What I'd like to say is that this is an inertial trajectory because we're going in a straight line in the same direction at the same speed. And I'm emphasizing speed here as a magnitude, the magnitude of the velocity, how fast we're going. But I should really also emphasize direction because we're also going in the same direction in a straight line. So that is an inertial trajectory. So that's it for the idea of like direction and forces. This is really the meaning of this equation. There's a component of magnitude, the magnitude of the acceleration, and a component of the direction. And inertial trajectories are trajectories that are smooth. Trajectories in straight line, this is really what we mean by inertial trajectories. But now I want to emphasize the idea of a force of the mass. I'd like to now emphasize the idea of the mass, and that will be the end of the video. And what is meant really by mass is the inertia. Now that's very strange. Why would you say that? The inertia. Of course, now mass is the inertia. When I say that a particle is going in a specific direction and I want to stop it, or I want to predict the next motion, or I want to interact with the particle in some kind of way, then the direction really counts, of course. Due to this part of the equation, the direction really counts. And this thing is going at a velocity v, which is a vector quantity. It has a direction, and it has a magnitude, how fast we're going. Okay, fine. But I want to also talk about the mass. I want to have the mass in mind in my thinking, because inertia, the sum of the force is equal to mass and acceleration. The idea of a mass is really important, and there's a way of thinking of mass as really uh, the quantitative factor of inertia. What do I mean by this? Suppose this mass is a truck. You know, that's a very ugly truck, but this is not a drawing class. Let's make it like a bit nicer. We have a little window here, and it has a mass m1. And let's see how well I can. So it doesn't really matter how nice the truck is. This is the worst truck in the history of trucks. But hey, like nobody cares about that. But what we really want to do is consider that in order to stop this vehicle, it's gonna take a hell of a. Look at this guy, bro. This is like Bob, and Bob is like trying to stop the car, and he's like pushing his hands forward, and he's thinking, okay, I'm gonna try to stop this truck, but he's not gonna do it because the truck has a lot of inertia, and what I really mean by inertia is not really the velocity, and I really mean the mass. And let me motivate this idea. Think about this. If there was an identical moving ball, in a parallel reality, and let's say there's another observer right here trying to stop this ball from moving. We have scenario A and scenario B. Think about this, like if I want to stop this ball at a velocity, which is, let's say it's the same velocity v, and I want to stop this ball in this dimension, well, it's very easy to stop the ball. I don't even have to place my hands. My belly might just do it. It might hurt a little bit, but I'll probably be able to stop the ball. If we're talking about like normal velocities, of course, like maybe like 50 kilometers per hour, like any normal velocity a vehicle is supposed to go at. Well, of course I'll stop the ball, but the reason why I'm able to stop the ball in the truck is not the velocity. Of course, they're the same velocity. The difference here is the mass. And this is what I mean by inertia. This body has way more inertia. And so, according to Newton's first law, which is a body is going to continue in a state of motion unless acted on by a force, well, this truck is going to continue at the state of motion that it's going at, because it's going to require a hell of a lot of force to stop it, because it has a huge mass. So inertia is not just velocity or acceleration. I mean, acceleration is supposed to be zero in inertial motion, of course, but in order to move something, it really depends on how massive the thing is. So we're going to consider that the inertia of the truck is actually its mass. The velocity counts. If the velocity is very high, it's very difficult to stop it, as opposed to a very small velocity. It does count, but mass also counts, and mass is really the invariant component of the inertia of the truck in all situations. Think about this, like, let's sort of like reflect on the idea of velocity and invariance in relativity and in classical mechanics. Well, in classical mechanics, the idea of relativity applies, and so it does, and so it is in special relativity. The idea of a frame of reference applies in all of physics, even in general relativity. When we're thinking about velocity, the velocity is going to be relative. It's going to depend on the frame of reference, but not the mass. And if suppose there's an observer going at the velocity v, and in scenario B, of course, let's say there's a bird. Well, according to the bird, the truck is really not moving because the bird is also going at the same velocity. You see, so the bird is really not moving relative to the truck. He sees the truck as something stationary, and the ground is probably moving in the opposite direction, according to the bird, going at velocity v. But the bird, in that frame of reference, will still not be able to move the truck because it's so massive. And so really what you really have to consider is that the mass is the invariant part of inertia, and velocity is really the relative part of inertia. Of course, it does count, but when a physicist talks about inertia in a very deep way, there's a paper by Einstein called "Does the inertia of a mass of a body on its energy depend on its energy content?" A very revolutionary paper. You might have heard of the famous equation E equals mc squared, where m is the rest mass. This is the result of the paper, but really what I want to emphasize is that in the context of the paper, he really meant mass as inertia, and it's really easy to understand it if you think about a truck, you know. If the truck is not moving, you're not going to make it move, probably on your own, because it's a lot of force to do it. And if it's moving, you're not going to stop it, because it's a lot of force to do it. So velocity is really relative and really doesn't matter in a scenario. The mass really does matter, and really you can think of inertia as the mass of an object. That's really it. That's the idea that I wanted to sort of like propose to you in this video. Thanks for watching the video, and I hope I'll see you in the next video.